fourth video in Stoichiometry Unit 8, and today we're going to be talking about mixing these problems up a little bit. And we've got a good problem solving graphic aid to help you guys, and it's really sort of cool. So don't run away, I'll be right back. Okay, so now we're going to be talking about mixed stoichiometry problems where we're looking at a lot of things. And if you look at our little graphic organizer, it really sort of helps you. And our first step in the process is to get everything into moles. If we get everything into moles, then we can use that mole ratio from the balanced equation to get the moles of the unknown, or what we're looking for. Then if we have the moles of the unknown, or B, if you want to call it that, then we can very easily convert the moles of B to the liters for volume, the grams for mass, or the particles if somebody wants to know how many are there, right? Okay, so it's just convert the known to moles. Mole ratio, find the moles of the unknown, and then we have moles of unknown, then we find the unit we're looking for. Okay, so not too bad. I lost my little yellow thingy. There we go. Okay, so if we look right here, this is what I just said. Convert to moles, mole ratio right there. Then we calculate what we need. That's all we're doing. Let's look at one. Here's another little graphic organizer. So if we're given grams, or particles, rather, if we're given particles, 3.21 times 10 to the 15th molecules of whatever, we use our Avogadro's number to get the moles of what we're looking for. They're trying to find, let's say, W. Then we take our balanced equation to the mole ratio and get moles of W. And if we're looking for the molar mass, we find the molar mass of W and multiply by that, and that gives us our mass of W. So I'll try to print out some of these just for you as a good little graphic organizer, a graphic aid. So here's a real world application. Tristyrene, C57H110O6. Okay, that's a triglyceride, or a three-chain fatty acid, or a three-chain fat. It's a type of fat which camels store in their hump, and they use it to make chocolate. Yeah, they really do. All right. So, for chocolate, we're making that. If you have 2 moles of tristyrene and 163 moles of oxygen gas, if you burn it, you're going to produce, all right, 114 moles of carbon dioxide and 110 moles of water. That's why they don't have to drink that much. So at STP, what volume of carbon dioxide is produced when 50 grams of tristyrene is burned by the camel? So they gave me the mass of the tristyrene, and they're looking for the volume in liters of the carbon dioxide. Let's see how we do it. So we were given 50 grams of tristyrene. So we're going to, for doing that little graphic organizer, that gives me the mass. Then I'm going to convert to moles of G, right? Dividing by the molar mass of G, which would be the tristyrene. That's going to give me the moles of G, so I'll multiply that by the mole ratio to find the moles of the W, or the unknown. Then I just have to convert that into using the molar volume ratio, 22.4 per mole, liters per mole, and that gives me the volume of the unknown, or the volume of carbon dioxide. So the molar mass of carbon is 12, the molar mass of hydrogen is 1, the molar mass of oxygen is 16. So I find the molar mass, 57 times 12 plus 110 times 1 plus 6 times 16 grams, and I do it. So 1 mole of, or the molar mass of tristyrene is 890 grams. That's a bunch. We got to do that first. So we know that's 890 grams. So to get the volume of carbon dioxide, we take our known 50 grams of tristyrene, multiply by the molar mass ratio, 1 over 890. Then we're going to use the balanced reaction. It's looking for every 2 moles of tristyrene right there. We produce 114 moles of CO2, so that's the mole ratio. Then we're going to multiply by the molar volume. Okay, so that'd be 50 divided by 890 times 1 times 114 divided by 2 times 22.4 divided by 1, and it comes up with 71.7 liters of carbon dioxide. So they're going to be breathing out a lot as they consume that fat in that hump. All right, so here's a good question, and I'll work it with you. Okay, just for a review. Get my little pen going. All right, so how many liters of water vapor can be produced from the combustion of 1 gram of glucose at STP? Okay, so they gave me 1 gram of glucose. That's glucose. All right. So we're going to need to find the molar mass of glucose. So let's do that real quick. So look at my periodic table. I know carbon is 12, so that's 6 times 12. Hydrogen is 1, so that's 1 times 12. Plus, I know oxygen is 16, so that's 6 times 16. If you need any questions on that, we'll talk about it in class. Oops, I got an error. Yeah, I didn't do that right. 6 times 12 plus 1 times 12 plus 6 times 16. I get 180 grams per mole. All right, let's set things up. So I have 180 grams per mole. Well, excuse me, I've got 1 gram of glucose. 1 gram of C6H12O6. Molar mass is 180 grams of glucose. C6H12O6 for every 1 mole. It's looking for the amount of water vapor. Well, I've got to use my water vapor, so that's 6. So now I've got 6 moles of C6, or 1 mole of C6H12O6. So if I look right here, for every 1 mole of C6H12O6, I'm going to produce 6 moles of water. And that's what they asked, right? How much water vapor? And it's asking for liters, so for every 1 mole of water vapor, there's 22.4 liters of water. So 1 times 1 divided by 180 times 6 times 22.4, I come up with 0.74 liters of water vapor. Okay? B. What is the mass of CaO, calcium oxide, that would be required to completely react with 42 grams of H2O at STP? So, let's see. Let me pause for a minute. We'll come right back. I want to think about this one. Okay, so the given is 42 grams. Oh, well, they give us the answer, but we won't do that yet. So let's go back. Let me get my pen turned on. Okay, so I've got 42 grams of water. The molar mass of water is 18 grams. Notice I put that on the bottom because it's got grams of H2O for every 1 mole of H2O. Okay? So we're looking for calcium oxide, and I see that I have a 1 mole for every 1 mole of water, I'm going to consume 1 mole of calcium oxide. So that's a 1-to-1 relationship. And for every 1 mole, it's asking for mass, 1 mole of calcium oxide. All right. On the periodic table, calcium is 40.07, oxygen is 16, so that's about 56 grams of CaO. And that's going to give me, let's see, I'll cancel out my units, because that's just a good thing to do, and it's going to leave me with grams of calcium oxide, and that's what it's asking, mass. So 42 divided by 18 times 1 times 1 divided by 1 times 56 divided by 1. That gives me 130, really 131 grams, but multiple choice, that has to be A. And of course, we already saw that's what it is. One last one. Okay. How many grams of ammonia can be produced by reacting 1 times 10 to the 1 moles of nitrogen gas, or 10 moles of nitrogen gas, with hydrogen gas at STP? So they gave me 10 moles. Cool. Write that down there. 10 moles. Times of what? Nitrogen. Times, now I just do my mole ratio for every 1 mole of nitrogen. 1 mole nitrogen. Okay, it's going to react with, I'm going to produce 2 moles of ammonia. All right. So for every 1 mole of ammonia, it has a mass of nitrogen is 14, 3 hydrogens, 17 grams NH3. And let's see, for every moles of nitrogen, moles of ammonia, it's going to give me grams of ammonia. So let's do our math. 10 times 2 times 17. I get 340 grams. Let's see if I'm right. And I am. Yay. All right, last one. How many grams of chlorine gas are needed to react with 1 mole of antimony Sb at STP? So I'm given 1 mole, and that makes life easy, of antimony. So for every 1 mole of antimony, okay, I've got 3 moles of chlorine gas, and it asks for grams. Cool. So for every 1 mole of chlorine gas, it has a mass of 35.5 times 2, 71 grams. 3 times 71 gives me, wait, 1 mole of antimony, 3 moles. So that's 3 times 71. Oh, my fault. That's 2. For every 1 mole of antimony, all right, for every 2 moles of antimony, I'm consuming 3 moles of Cl2. So I'm going to divide by 2, and I come up with 106 grams, or 106.5. Let's see if I'm right. Oop, I am. See, I go, oh, I lied. There's about 2 more. So, how many moles of aluminum oxide are produced when 3.58 kilograms of magnesium dioxide are consumed? Well, I want to fool with grams, so 3.58 times 1,000. That's what the kilo stands for, if you recall from our earlier part of the year. So I've got 3,580 grams of magnesium dioxide. All right, how many moles of aluminum oxide, Al2O3? So I've got 3,580 grams of MnO2 All right, I need to, magnesium has a molar mass of, we find it, 54.94 plus 32, 16 times 2, that's 86.94 grams for every 1 mole of MnO2. All right, so for every 3 moles of MnO2, I'm going to produce 2 moles of aluminum oxide, Al2O3. See, that got me where I want it. It does. It'll give me what I'm looking for. So 3580 times 1 divided by 86.94 times 2 divided by 3, I got 27.5. See? And I got it right. Okay, guys. That's stoichiometry. Again, the math is not that hard. And we'll be doing a lot of practice with this as we go throughout our time. And so anyway, this is Coach Scott saying we'll be talking about limiting reactants on the next video. So Coach Scott saying deuces.